We're going to start looking at polynomial functions. So believe it or not, your quadratics are actually a subset of your polynomial. So our definition of a polynomial is that we're going to have n be a non-negative integer. So that means it's going to be numbers like 1, 2, 3, non-negative integer, so 0, 1, 2, 3, on and on like that. And we're going to have a sub n minus 1, and then it would keep on going to a sub minus 2, basically like an a5 and then an a4, and then we go a3, a2, a1, a0. Or maybe we started a6, but like that. Or let's say indexing is what it's called. But these are going to be real numbers. They're going to be coefficients. But they're going to be real numbers, and the first one cannot be 0. Because otherwise we're just making some function that kind of nonsense at that point. The function is going to be defined for a polynomial is that we have an times xn plus an sub 1 times xn sub 1 plus, that's the typo there, plus a2, it was supposed to be dot, 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 and I should have got an L there, a2 x2 plus a1x plus a naught, or a0. This is going to be called a polynomial function of degree n. So notice that n is the degree of the polynomial. The number an is going to be the coefficient of the variable with the highest power, or what we call the leading coefficient. So another way, an example of this would be if f of x is equal to 3 to the 5th plus 2x to the 4th minus 11x to the 3rd plus x squared minus 7x plus 33. So this here would be your A5, this would be your A4, this would be your A3, your A2, your A1, your A0. So that's what's supposed to be representing, is that there's different coefficients on the different parts. And here, the degree is going to be 5, because that's the highest term here, and your leading coefficient is going to be the 3x to the 5th. So when we graph a polynomial function, it's going to be a smooth, continuous curve. Meaning, it could be something like this, like we have with the quadratics, or it could be like this. It could be like this. Just as long as it's smooth and continuous. So polynomial functions of degree 2 or higher have graphs that are smooth and continuous. These are all degree 2 or higher. By smooth, we mean that the graph contains only rounded curves and no sharp corners. So when we talk about something being continuous, this is the least formal definition of this, but continuous for us for algebra means that the graphs have no breaks and can be drawn without lifting our pencil from the rectangular coordinate system. Basically, it's all interconnected. There's no breaks or anything in it. So what we have here is polynomial functions are always going to be smooth and continuous. So end behavior of a polynomial function, the behavior of a graph of a function to the far left or to the far right is called the end behavior. So like I said, if I graphed a polynomial like this, we're talking about end behavior, whereas we're talking about what goes on here and here. That would be end behavior. So although the graph of a polynomial may have intervals where it's increasing or decreasing, the graph will eventually continuously rise or fall without bound as it moves left or right. It means it might bump up and down like this, but at some point, all your polynomials hit a point where it just keeps going down or just keeps on going up. The sign of the leading coefficient, that an, and the degree of the polynomial is actually what we can use to identify end behavior. So what we're going to do is we're going to create something called the leading coefficient test. And once again, that wasn't supposed to be there. It's supposed to be dot, dot, dot. But as x increases and decreases up bound, the graph of the polynomial function sorry, a sub n, x sub n, blah, 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 a sub 0, eventually rises or falls, in particular the sign of the leading coefficient and the degree of the polynomial from the end behavior. That's what we call the leading coefficient test. So what we were talking about before. So before we do this test, let me move into decimals. So if you look off to the side here, I have three functions, but notice they all have the same leading term. That leading term is 3x to the fourth. So right now I just have a couple of them graphed. So if I graph the bottom one, 3x to the fourth plus 10x to the third minus 3 is going to look like this. So we see it kind of bounces around a little bit. That's g 3x to the fourth minus 5x cubed minus 3x squared plus x minus 4. And that is just 3x to the fourth. So they look like completely different graphs from here, right? So when we're talking about end behavior, what we're talking about is that we see it bounces a little bit in here, but we want to know what happens at the ends. We see a little bouncing here, what happens at the ends. So let me rescale this. Like I said, close up, they look completely different. But as I zoom out, notice they start pretty much looking the same. All those lines are laying on top of each other. So what's happening here is that this leading term overpowers the rest of the function, and all of these, regardless of what else is going on, long run, all behave just like 3x to the fourth. They're just going to behave like that part right there, that part of the polynomial. Okay. So let me erase all this. The other thing we're going to show you here. So here I have x to the fourth, x squared, x to the sixth. Put it, change the order there. Well, what's important is they all have a even power. So notice we have even powers, they all have this basic function, basic shape to the function. Also, they all have a positive coefficient because if there is an a out front, they're all going to be positive. Let's make them all negative and see what happens. So you notice when it's a negative coefficient, then everything is opening down. So if we have an even power, it's still going to be that parabola shape, except now when the coefficient is negative, it's going to open down like this. Now the next thing we're going to do is we're going to change that power. So like I said, these are all even powers. So we're going to see what happens when we have negative powers. Or not negative powers, I'm sorry, odd powers. So we'll make this 3, make this 5, and we'll make this one 7. So notice when they're odd powers, we're getting this kind of basic shape. It starts down here, it does a little curve, and then it goes back up. In here, a is positive again. Now if we make a negative coefficient out front, now we see it all flips again. But we're still getting that same basic kind of shape there. It's still that like little snake curve. So this is what we're going to be part of our leading term test. So leading term test is basically this. If we look at the leading term of our polynomial, which is always going to be of form an plus x to the n, that is always going to be the leading term. So the leading term is going to be the term with the largest power. And if we write everything in standard form, that would be the first one, but if it's not, just look for the one with the largest power. And what we see here is that we're going to have this kind of basic shape here. So the leading term test is, this is for n is odd. So this would be something in the form of x cubed, the fifth, the seventh. But when it's odd, we're getting that snake curve again, right? So you're like this or like this, except there could be some bouncing going on in there. But what we're concerned is in the end, what's going on. In the end, what we should see here is that if your leading coefficient is positive, so a to the n is positive, what we should see is leading, our end behavior is going to be acting like this kind of curve. So it's going to have that snake shape because it's odd, and then it's going to be starting from negative values and then keep increasing. If, however, a to the n is negative, like we have on this side, remember that right there, then we see that this is going to flip and it's going to have like this basic shape. So even though it might bounce a little bit in here, at the end, this side is rising, this side is falling. Now, if n is egg and even, geez, that's like if we have x squared, x to the fourth, x to the sixth. What we have here is these basic shapes. If the leading coefficient is positive, the graph is going to rise to the left and rise to the right. So if a to the n is positive, then we got a parabola opening up basically. So there might be some bouncing here, but long run, we see it's rising at both ends. If our coefficient an is negative, then it's going to be a parabola opening down, essentially. There might be some bouncing in the center, but at the ends, everything is falling down. And that is what is leading coefficient test. So we're going to use the lead coefficient test to determine the end behavior of fx equals 4x squared plus 4, x to the fourth minus 4x squared. So leading term, so one with the highest power, so it's going to be this x to the fourth. That means the leading coefficient is, there's an invisible 1 in front of this, right? Your leading coefficient is going to be a to the n equals 1, which is positive. Then when we go with the power, we have a even power. So what we're saying here is that we know that this is going to be, in the end, we don't know what's doing in here, but at the end, we know that it's either going to be a parabola shaped like this, or at the end, it's going to be a parabola shaped like this because of the even power. Because this is positive, it tells me is the shape I'm looking for. Let's graph it and see if that is actually my end behavior. And when we graph it, it might have a little bit of bouncing around in here, but the end behavior is going up at this end, going up in this end, just like if we had a parabola. So it's telling me that end behavior. So without graphing, use the leading term test or your leading coefficient test to match each of the following to one of these graphs. So you have 4 equations, you have 4 graphs. Like I said, worrying about that leading term, so the one with the highest power, that is going to tell you what the overall behavior is. So if you know what the end behavior is, you can identify the correct graph. Okay, so remember, if you have an even power and your coefficient is positive, you should be opening at the ends. If it's even power but my coefficient is negative, we're going down at both ends. If it's an odd power, but A is negative, it falls here and rises here, so it's increasing generally. And if AN is negative, then we're going to start here and fall like this. So if we go back and we look for our leading term, get a new color for that. So if we look at A, this is my highest power term. If we look at B, this is my highest power term. If you look at C, this is my highest power term, and F, this is my highest power term. So the ones in the little box right here, those are all your leading terms. And what we see here is that we have here's my color there, an even power. So we know we're looking either this graph here or this graph here. And we see that the coefficient 4 is positive. So our coefficient is going to be 4, which is positive. So we know that we are looking for this situation right here. Graph that matches that is going to be C. So this goes with A. So this is graph C. Now if we look at B, we're going to see that we have an even power again. But this time we got a -1, so my coefficient is a -1, which is negative. So it's even, but the coefficient's negative, meaning we're looking at this place right here where it opens down at both ends. And the graph that matches that is B. So graph B matches with problem B or equation B, function B. If we see that we have an odd power now, and our a to the n is going to be, an is going to be -2, which is negative. So odd power, but an is negative. We're looking for something like this. So going up on the left and going down on the right. We see that in D. So this graph D matches with C. So this one we kind of know by default, but just go through it anyway. So for D, we got 6x cubed. So our odd power again, but a to the n is going to be 6, which is positive, meaning we're looking at an odd power, positive coefficient. We're looking at this situation where on the left it falls and on the right it rises. I'm finishing this with graph A. All right, you're going to work on worksheet number 2. So you're going to do leading coefficient test, which is determining the end behavior of this 3x minus 2 times x plus 2 times x minus 1. So this is not in the form you usually see. We're usually seeing something that, is different terms. So take a minute and work on how you think you might work on this, and then we'll go back and see if there's maybe an easier way to do it. So I'm assuming that some of you just expanded. So if we expanded this, what you should end up with is qx is going to be 3x cubed plus x squared minus 8x plus 4. So we see that my leading term is going to be 3x cubed. We know from this we got a odd power and positive coefficient. So we are expecting that the end behavior of this is going to be like this. Second, I'm trying to get the graph up. So actually, if you graphed it, get my points here. That one's 4. So it kind of does this. Oops. I think it just does this. Sorry, it's not drawing smoothly. That's what the graph of it vaguely looks like. I'm sorry, that's the best it's working right there. But like we said, it's got that basic shape where we said it's going to be kind of like that cubic curve. We just don't know what's happening in the center. Now, alternate way to do this. So we just need that coefficient, right? So if you took the 3x minus 2 times x plus 2 and the x minus 1, and if you really just looked at each one of these segments, these numbers all got multiplied together, right? That's how we ended up with the 3x cubed. So if we just take that part and we multiply it together, so just basically take the leading term of each one of our factors, that's also going to give me 3x cubed. So that also gives me my leading term. So another way to find your leading term is you can expand everything like this, or you just take the leading term of each factor. So take product of leading term of each factor. To find just your leading term. And if you had something up front, like you had a 5 here, then you'd have to put that 5 there because that power needs to go along as well. Or not that power, that coefficient. Because you're treating that once again like it's just another factor and you're taking the leading term. Okay, so zeros of a polynomial. If f is a polynomial function, then the values of x for which fx is equal to 0 is going to be called the zeros of f. So this is that difference of, we were looking at, say, quadratics. So this here, what we're going to say is that f of 0, wherever f of 0 is going to be, or sorry, whenever f equals 0, x are the, what we call the roots of fx. We also call them, my solutions there, x are the solutions of x cubed minus, or sorry, x squared minus 3x, got an extra square there, minus 2 equals 0. Just kind of make a little bit of a difference here, what we're looking for. Or the other thing is that we say, don't know why that disappeared. Or you could say that x are the zeros of fx. But another way of looking at this is that x's are going to be your x-intercepts. So these values of x, like I said, are going to be your root solutions, zeros, x-intercepts. Each real root the x-intercepts only as long as x is real. Each real root of the polynomial equation appears as an x-intercept of the graph of the polynomial function. So you can have roots that are not real numbers. You can have solutions that are not real numbers. You can have zeros that are not real numbers, but your x-intercepts have to be real numbers. So we want to find all the zeros of this function here. So what we can do is we can factor. We're going to look at different factoring techniques. So one of the things we can do here, we got 4 terms, we can factor by groups. So I want to find all my zeros. What I'm looking for is that I want fx to equal 0, meaning that I want x cubed plus 2x squared minus 4x minus 9, or sorry, minus 8 equals 0. So this is always your first step, is if you want to make this set equal to 0 if I'm looking for my zeros. And like I said, we do factoring by group, so I can factor out an x squared from x cubed plus 2x squared, leaving me with x plus 2. I can factor out a 4 from 9 minus 4x minus 8, leaving me with an x plus 2. X plus 2 can be factored out, leaving me with x plus 2 times x squared minus 4 equals 0. And then I could factor that further into x plus 2. This is a difference of squares. So that's going to be x plus 2 times x minus 2 equals 0. So this isn't much different than what you've seen with polynomial. What we have here is that either x plus 2 equals 0, or the other one, x plus 2 equals 0, or x minus 2 equals 0. So we solve these, either x is equal to negative 2 or x is equal to 2. So we don't write solutions that double. Our solutions are our zeros. Are x negative 2 and x is 2. Remember, these are also x-intercepts. We'll graph this here in a second. If you look at here, where are my x-intercepts? There and there. So my x-intercepts are negative 2 and 2, which are also my zeros. So we call them zeros because that is when the function is at 0. So it's when y is equal to 0. And remember, those are also roots. Work on worksheet 3. So you just want to find the zeros of both of these. So right now there are quadratics. So you just need a factor. Okay. So we want to find zeros. If we factor this, I just need 2 numbers that multiply to give me 6, but add to give me 5. It's because we're trying to solve x squared plus 5x plus 6 equals 0 if we want to find our zeros. So we would have x plus 3, x plus 2, because those add together to give me 5, but multiply to give me 6. So either x plus 3 is what equals 0, or x plus 2 is what equals 0. So x is either equal to negative 3 or x is equal to negative 2. So my zeros are x equals negative 3 and negative 2. Now for h, we got 3x squared minus 7x minus 6, and we want to find the zeros. So we make that equal to 0 because we're looking at hx equals 0. So just for practice, you can still use quadratic formula. Because that's still looking for those x values when this is set equal to 0, because that's what quadratic formula does. It solves this. So we get minus b plus or minus the square root of b squared minus 4ac over 2a. So x is equal to a negative b, so b is negative 7, so it's going to be plus 7 plus or minus the square root of negative 7 squared minus 4 times a, which is 3, and c, which is negative 9. All over 2a, so 2 times 3. So to save us a little space, I'm going to just figure out what is under the square root. So we have a Negative 7 squared, which is 49, minus the 4 times 3 times negative 9. So it's going to be 7 plus or minus the square root of 157 divided by 6. We may have tried factoring this and it wouldn't have worked, because this is going to basically give me two solutions that are, if you're going to be exact about it, my zeros are x is equal to 7 minus square root of 157 divided by 6, and 7 plus 157 divided by 6. Or if I want to get an approximation here, that's negative 0.92 and approximately 3.25.